Portugal IOCS in 2017. And the link you get is directly, the link you get on the website is direct to the talk, to the PDF of the talk on the IOCCG website, which is great because there's a ton of copyrighted material here that we can put on, and someone has already taken care of it for us. This is really, really exciting. It's really exciting in the sense that this is one of the great next thing we're going to hopefully have to do oceanography with, namely LiDARs. People have used them through the years, and I'll talk a little bit about their history, but it's new, it's different information, and together with polarimetry, it's really the next thing to, and hyperspectral, and UV, etc. These are the amazing new tools that you guys hopefully will get to play with them. So when you think about passive ocean color, just radiometry, there's some issues. We know that the signal is dominated by atmosphere, the signal at the top of the atmosphere. We're only penetrating to a small part of the surface. We don't get information about layering. If there's a vertical structure, we don't know about it. It's an optically integrated, and each wavelength penetrating to a different depth. There's issues with aerosol clouds, solar angles that are affecting your signal, and there's no information at night. You're dependent on having the sun. In comparison, what LiDAR could allow you is a signal from a known source, so you're controlling your source. You have a constant viewing geometry. You all the time look at the ocean from the same direction. Minimum atmospheric correction issues. It's time gated, and I'll talk about it in a second. It can penetrate relatively deep into the photic layer, resolving vertical structure. Can separate absorption from particulate scattering. So you can get two parts of the signal, the attenuation part, which is mostly due to absorption, and the scattering part. You can go through thin clouds and aerosols and sample in between clouds. And you can sample in the day and at night, because you have your own source. So both of them can be done. So that's because it's an active source. So first I'll go through how it works, some notes about measurements in the field, the idea of putting something like this in space, some example of some science questions, and the prospect forward. So how does a LiDAR work? LiDAR has a strong laser, and then there's a telescope, and it's sending a pulse down into the water column. It's scattered along the way and in the water, but at the time when it gets to the receiver, so the receiver is range gated, so you're getting different signal at different time. The first signal you get is backscattering through the atmosphere. You're getting a very strong response from the ocean surface, and then you're getting a signal that depends on the scattering through. So this is a trace in time, which is represented as a trace in depth of the power getting into your detector. So it's range gated, just like the radars that are used to look at clouds and other things. You can get different polarization state, and these are important, and I'll talk about it in a second. Typically, you're using a YAG laser with a fundamental wavelength of 1064 nanometer, and then frequency double to 532, which is a green laser, and then 355, which is in the UV. So you can actually get all three frequencies. Lasers are polarized sources, and you can, again, look at the detection in cross and copolarized. You can detect fluorescence, meaning if you shine here, you can, and have a detector in the blue, you can look at CDOM. With 532, you can excite chlorophyll, and people have done it. So you can get chlorophyll fluorescence.
You don't excite chlorophyll, you excite accessory.
You excite accessory pigment that transfer energy to the reaction center and then fluoresces from photosystem 2. But sorry, you're absolutely right. Yeah, you can filter as spectrally as much as you can. I'll show you that helps a lot in the new one of the new ways to use them to get backscattering, and you get this sampling in the vertical that depends on. I mean, what's this limited your resolution here depends on the amount of signal you want to get. So your size of the antenna, how much energy you're pumping down. And in terms of energy pumping down, one of the requirements is that it be eye safe. So you cannot go and burn boats in the ocean or people or whatever. So that's a major issue. But again, you can scale the telescope accordingly up to a certain point because you don't want to fly a huge bus in space. These are all constraints that people. But it turns out you can come up with reasonably to a 3-meter resolution. And I'll talk about it later. So here is an example from this is a special LiDAR, an advanced LiDAR from Langley that has been mounted many times on airplanes. But just to show you, you can get the aerosol backscatter, so you can study smoke plumes coming off Nova Scotia here, and marine aerosol. And then in the same time as you're doing this, you can probe the ocean, because that signal comes after that signal. And look at, here you're getting strong scattering. This is, if you will, these are the attenuation in the water, but this is due to resuspension in shallow, relatively shallow banks, and then further here it's get bluer and bluer and lower attenuations. Yes?
The black, that's not the bottom.
This is the bottom. Oh, sorry, this is the base from where they don't get signal anymore.
Okay.
This is the base of the signal. It could be bottom if there is a bottom. And
High attenuation, so it's probably.
yeah, and it depends where you are. I mean, obviously, yeah. But it's if the more attenuation you have, the less deep you penetrate. And so you're absolutely right, Colin. Thank you for the correction. What else can I say about it? Yeah, that would be it from now, unless you have questions. Yes.
What limits the source wavelength? Like, is it
Oh, so it's a kind of the technology. So this is one of the first kind of laser ever created were these lasers. So they're well known, well characterized. Now you can get laser in any wavelength you want. But I'm not sure how much energy you can pump and how much you lose in terms of the conversion and things like that. But this is really the classic.
And they're the strong, I mean, they're one of the strongest ones, so the yak lasers. Yeah.
They are eye safe.
So they don't have to be. That depends on how much energy you put in. The requirement is that it has to be, if you use it, when they use it in the field from this airplane, they should not kill people or make them blind as they fly over. I mean, that's part of, so yes, they have to be eye safe. At the distance where you're turning it on. So, you know, if the person is right at the place where the laser comes out, probably, but when they flew over us, we were in a field campaign and they came several times over us as they were sampling. And I don't think they turned it off. So the history is actually quite long in oceanography of these measurements. It starts with 73 where they did chlorophyll fluorescence, or again, what we said before, it's not the chlorophyll, but the photosystem fluorescence. A very big player was Hogue. He had a system mounted on an airplane where he looked at, he used Raman as a scale factor. So the Raman emission gives you how much energy actually went to the water, which is important because temperature can change how much you're pumping out. And then you're normalizing the chlorophyll and phycoerythrin they were looking, because 532 can excite phycoerythrin in distribution across lines in the ocean. They also were looking at, Hogue had a paper in 88 where he was looking at backscattering and attenuation. So now he's looking at particles more by looking at the signal at the same wavelength as 532. Again, paper on CDOM, more about photosystem, etc. So it's a measurement that has been done, but only from airplanes and from boats. There's some system, NRL has a system that they basically, along their trajectory, they have a laser on a boat, and I know that Dick Zimmerman from ODU has built one as well, that they're using in Chesapeake Bay to do measurements in the water with their LiDAR. So it's not, it's not revolutionary as a technology. Churnside for years have been doing a sardine survey on the west coast where the signal, there's so much fish that he can count the spikes and those tell him about the depth and the amount of fish in the water. So again, and there are companies, and you can find them on the web, they will map bottoms. If the bottom is shallow enough, they can map the bottom with a LiDAR. When the beam is narrow enough, they do surveys and it's relatively cost effective in many places to map the bottom. So the question is, can we do it from space? That's the big leap. And the big leap actually happened with several sensors. The first one, a LiDAR in space technology called LIGHT, put on the space station, 3 wavelength, get the NAG LiDAR. So this is how much energy was pumped out in each one. Multi-angle, so they look and do, and some of the time, so most of these sensors, all of them, were really not designed to do ocean. They're designed to do atmospheric aerosol. But when they looked, they found signal coming from the water, from under the water. They're not designed, they have very relatively large time integration, which means that you're getting about 30 meters of water as opposed to 3 meters that I'll show you afterwards that it might be possible to do. Then there's this sensor called Calliope, Cloud Aerosol LiDAR with orthogonal polarization. It's a collaboration between NASA and CNES. It's on, if I remember correctly, it's on a European satellite, launched in 2006 and is still active today. So data is still collected. Not designed for ocean application. We'll get there. There's 2 wavelengths, 532, 1064, 3 channels, so there's a copolarized, cross-polarized 532 and 1064 in terms of the detector. 1 meter telescope size, so really large. The 100 meter footprint. So you're getting a signal from 100, but often you have to integrate that for longer to reduce the signal to noise. 30 meter in air, that's the vertical, what you integrate, and 23 meter vertical resolution in water. Polar orbiting, 16 days repeat cycle. Measured both day and night. So you're getting measurements in the day and measurements at night. Let's see what that is. So here is an example of the trajectory, this 16-day repeat cycle, how it looks in terms of coverage. So obviously this is much less than what you'd get with MODIS, but you can get it in the poles at polar light. You can get it at night, which then has other advantage. And this is one of the pioneer of transferring this technology to the ocean. So this is, again, done for atmosphere. And then somebody says, well, I'm getting a signal in the ocean that I think means something from the ocean signal coming out. This is one of the first, his name is Yongqiang Yong, who is in NASA Langley. It's not far from where the next ocean up is going to be. And he's starting to look at the signal coming from the ocean. And when they share them with Mike Barenfeld, they see things that look like patterns you've seen before for IOPs, for the signal coming from the ocean. 2 papers, one in 2013 by Churnside, which evaluate the detection and compare it to MODIS, and there's another by Barenfeld in GRL, comparing with field validation and some geophysical products. So now let's move to some science. I moved too fast? Yes, I moved too fast. Come on. Yeah. So they flew. These are field testing retrieval where there's both ship in situ, Calliope, and MODIS. And they're doing a track, and you can see that they're corresponding not too bad to each other. This is the BBP times 10 to the 1,000 time backscattering. And what the sensor measure is not backscattering. It's something akin of beta pi. So beta in the retro direction. It's because this is what makes it back. You're not getting influence from the VSF in all directions. But as long as this, you can derive a relation between this and backscattering, this is where uncertainties come in, you can try and estimate what BVP is. So these are as function of latitude. Here you see in different days as function of local time, the passage and what's observed. And overall you see that there seem to be some agreement between all of the above. So now it's comparison between, so Mike has been working for years, and I've been working with him on it as well, is trying to get to phytoplankton carbon, relating phytoplankton carbon to BVP. So much of what you're going to see might have a phytoplankton carbon axis, but it's really backscattering. There's a linear relationship that was derived between them, so you don't have to believe it's phytoplankton carbon, it's backscattered. That's where it comes from, just so you know where it comes from. So here is ocean color versus LiDAR. And this is so what you can do, what people often do when they compare things that are not done necessarily at the same time, and the same, because as you know, the LiDAR takes at least 16 days to get a coverage, and these I think are seasonal cycles, or at least it's a yearly average, is you can compare histogram of distribution. And just to see, am I getting the same? So this is a QAA inversion, one of the inversions you learn about. This is the GSM inversion, and this is the Calliope distribution of backscattering, or particulate organic carbon in this case, but again, as function of frequency. So that gives you a sense, am I getting something similar or not, again. And this is from measurements, and this is what we have in measurements in all of the databases in terms of backscattering at that time, and this is again the Calliope. So one thought is one could use this system to anchor more backscattering because we have such a dread of backscattering measurement in the ocean, if indeed this provides us a good estimate of backscattering. Now a place where it could contribute the most are the poles. Why? Because at the poles, you have conversions of longitude, which means you get many, many, many more passages than you'd get anywhere else with a polar orbiting satellite. You get more measurements here because of all this crossing of path. You can see at the equator, they diverge the most from each other. So this is one advantage of going to the pole. The other is you're not dependent on sun angle. The poles, near the pole is where we have holes when we use passive radiometry, because there's times of the year that the sun angle is either too low or non-existent. It's permanent night. So at those times, the LiDAR still takes measurement. It doesn't care about the sun. So in this paper, we compared, we did several things. One is compare Calliope to MODIS, but also look at the trend in backscattering at the time of the year where MODIS cannot provide you data. So here is phytoplankton biomass as function of time, and you can see that the two follow each other really, really nicely. And these are in the regions where you can compare them because there's coverage all year. So that's the comparison region out here. This is for the southern hemisphere, so around Antarctica. This is around the Arctic. Yes?
On the biomass plots for the Calliope,
Yes.
the maps, are we looking at, those are dots where measurements were from some?
So it's 8-day composite, I believe. Or no, it's more like monthly. So it's a monthly. Each one represents a month.
For the Calliope?
For each.
For each.
Yeah. And they're done on relatively large. I mean, this is an average over this all.
Right.
So it's really large scale average.
And you're getting a 16-day repeat, so it's essentially 2 data points per pixel or per.
Per Calliope, while for MODIS you probably get, every day you get an image, at least in part of it. But actually you're getting more because Calliope will give, since you're comparing it here, each point is every 16 days, but you're getting many points. So it's easy to compare.
But the actual curtain is showing is really narrow, and these dots are obviously they're scaled out. They're gridded bigger than they actually are. Is
Oh yeah, for sure, for sure. But each dot is a place where you have a measurement with Calliope, just to show you where you're getting measurements.
Thanks.
Okay, so here is in the polar zone where there's all these gridded places. This is where you don't have data from MODIS, but now you have data from a LiDAR. So you're suddenly getting data in places that before you didn't have data. You assume nothing is happening. You didn't know. Yes.
It suggests that the biomass in the wintertime is really high.
Yeah. The backscattering is high.
Yeah, so I mean, if you did it in terms of chlorophyll, I don't-
Yeah. I mean, it'd be great.
or if you looked at the actual backscattering coefficient, do you have that data? I mean, since you did the conversion, you could,
Yeah. The data in backscattering is available, and actually,
which would actually be more interesting because
Yeah.
it has less assumptions.
and we're starting to compare them. We now have data from profiling floats, particularly in the Southern Ocean, from these regions that we can compare directly with the Kelsey. And that's what Kelsey is doing, including those that profile under ice and then come out and tell you. And surprise, surprise, there's always chlorophyll under the ice.
Yeah.
So detectable and backscattering. Yeah. So
Can the LiDAR penetrate ice?
no. No.
But you would look at ice thickness from the return time.
So there are LiDAR designed to study ice, one of which is IceSat, two that just recently, I mean, I think last fall has gone up to space. And there's others, and yeah. So there's amazing science to do by combining all these satellites together and looking at differences, similarities, what can you use one to add in terms of information to others. They're looking for people for the science team, actually. So if those of you are interested in polar. Anyways, this suggests that we have a new tool to do work, oceanography work, from space with a satellite that was never designed to do oceanography, which is really cool. Now, the type of science that Mike and I have been really enjoying doing is and this satellite has really helped us with as well, is looking at rate of change of biomass in the ocean, like what we call accumulation rate. So how much do phytoplankton, assuming these are phytoplankton, increase or decrease through the year, through the cycle of growth and loss? And what you see is that the biomass accumulation rate is here in these low latitude, in the North Polar Zone, start around. This is January, so just before March you become positive, you start accumulating, and then your climax in terms of accumulation of biomass is around May, and then by July you're starting to lose biomass. So this is also the time where you have maximum biomass. So if you look at it in terms of biomass, this is the cycle of growth and loss. The climax is when you're not accumulating anymore. That's the high. Maximum increase rate is during this period, is where this is steepest. This is the maximum decrease. And the initial rise starts very, very early, where just a little bit of light starts shining, you're starting to accumulate biomass. If you do the derivative of the annual, so this is, sorry, what you have here is not biomass, this is division rate. So this is estimated from primary productivity models. So primary productivity model, this is what they're going to give you as division rate based on chlorophyll, the light available, etc. If you take the derivative of this, it looks almost identical. They have different units, day to the -2, one of them, the other one day to the -1, but they're almost on top of each other. And what this suggests to us, and we did a little model to confirm it, is that grazers and phytoplankton are right on top of each other. So the grazer are in about, you can describe very similar curves by having zooplankton hit phytoplankton with a phase lag of between a few days. They're always riding behind. Which is amazing. Very simple math. Very, very, very simple math. It's in this paper. So there's a very close coupling between grazers and grazing. So to summarize, what Calliope has done for us is, despite the fact that a lot of people in the past proposed LiDARs for ocean, nobody took them seriously. And thanks for an atmospheric sensor, we are now able to say we want one for the ocean, but we want one that's optimized for the ocean. It's global observation, it's an independent assessment, in the sense that it has its own, it has different assumption, different measurement than what we do with radiometry, so we can really validate independently in terms of closure what we're measuring with MODIS with this tool. Provide us polar observation in places where we cannot have them, filling gaps between them, and also filling potentially gaps in cloudy areas and other. And again, help us with this ecological insight into what's happening with phytoplankton blooms. So this is, we're not there yet, but this is what we really want. We want to see a LiDAR in space for us. So what problem we have to solve? Is moving from an old sensor, just like we moved from CZCS to what we have today, and hopefully PACE, moving for something like Calliope to the thing we want. So one of the problems with Calliope is you have one measurement, which has the attenuation and backscatter, but you're trying to get two unknowns. You want to get, you have the backscattering, which is what happens if I go back. So the signal, as it propagates through the atmosphere, let's see, it was here. No, it's when I just showed the LiDAR here. So you have an attenuation of the signal until it gets to where there's a backscattering event, and then there's a backscattering event sensing back, and then it attenuates on the way up. So you have two attenuation and a backscattering event, assuming single scattering. So this is what your signal is made up from. And you have to try and entangle all of those. Let's see, maybe I can do it faster. Yeah.
Is the technology improved now to detect the time lag between the LiDARs and the laser signal?
That's how you do the time lag. The time lag is what's giving you the depth. So I'm integrating from here to here in time. This represents a certain depth horizon, again, assuming single scattering. Yeah, that's how all range gating systems work. So, but I have two unknown and I have only one measurement with Calliope. And you have to make assumption on how these are related. So you can come up with some ancillary data or biooptical relationship between these two, but these lead to large possible errors in your estimate. Yeah, so and in addition, because of these relationships, some errors accumulate along the way. So we'll have a much better signal if we could separate these two. And the question is how to do it. And people have done it already, again, in a thing called high spectral resolution LiDAR, HSRL. And the way they do it is as follows. Is there another scattering that was mentioned, inelastic scattering mentioned by Ken in his talk, which is called Brillouin scattering, and which you get from water. The water does it. And that causes a shift in scattering just due to the water. So now, a shift in spectral shift. So now if I follow the signal coming out from that scattering up in space, if I can separate this one from the one that's coming from backscattering and water in this angle, from the elastic scattering, both are attenuated about the same way down and way up. So I can separate, I'm getting two estimates of attenuation, but this one, I know what it is for water, and so I can separate attenuation and backscattering, basically with two detectors. So I have one detector looking at this channel and one molecular scattering, looking at those, which are separated. They're very close, but they're separate enough that with high spectral resolution, I can look at the signal coming from the water only versus the signal coming elastically from water and assuming there's no difference in attenuation in the atmosphere and the ocean for these two wavelengths that are extremely close to each other.
How close?
0.3 nanometer. Yes. So I can do the math and separate the two. So this is basically the math. I have a signal that's due to the particle, a signal due to the water, and they attenuate the same way. And from this, I can, from the two signals, separate the part that's due to scattering from the part that's due to attenuation along the path, which is mostly absorption dominated. This is absorption dominated, this is scattering dominated. Now I get, and that's a well posed. And this is example of ocean retrieval. They use HSRL for many things. These guys do. They fly in the Amazon looking at forest fire. They fly all over the planet. But these are campaigns they've done in the ocean. Some of which, these ones I was on, they basically flew with their big airplane above us and around us. Sabre is a campaign that Ivona led, where they flew along this part of the coast. And just to look at the type of signal they can get, this is an in situ profile of IOPs, and this is HSRL. And this is as a function of optical depth. And they get about, with this system, which is on an airplane, they can get a 1 meter resolution. It's not the same as putting it up in space. You can see good relationship between backscattering from HSRL and the in situ one. And the KD, again, these are different from the backscattering between the two. So these are the two things they separately get. So we get accurate retrievals of backscattering and KD. Backscattering, again, beta pi, so there's another conversion going in. There's obviously differences because the airplane is not exactly on the boat all the time as it's sampled, so there's near each other, not exactly on top. You're getting 1 meter resolution from the airplane. You get down to 3 optical depth, which is great. So now you can possibly look at structure, at least the top of the chlorophyll max. And some studies suggest that by using these more realistic vertical structure, you can improve primary productivity estimates. So where are we going with that? So if we could design one for the ocean, I mean, this is a great rendition. These are different kind of from just different kind of satellite missions for ocean that one could suggest. And so now we're getting into the realm of politics. Because it's now being pushed all very strongly, but with a lot of resistance from the atmospheric community. If we added, why?
Why?
Because it costs money. And if they have a mission for aerosol, and it has a certain cost that they were allocated by the decadal mission, why would they invest in something that's more expensive just because the oceanographer?
The atmospheric community to
Yes.
change their sensor as opposed to asking the ocean community.
Well, we got PACE. We in the U.S. again. In the U.S. we got PACE. That's our next story. That politically we were awarded in a variety of reasons coming from a previous decadal survey. PACE was pre-ACE. ACE was a aerosol mission. From their perspective, the atmospheric people think we stole it from them. Some of them, not all. Some think we stole
They have to
that
be
mission.
out
And
I know it was. Free.
yeah, and this is why we have only 3 years of PACE, with potential for maybe 10 years max in terms of the amount we get.
Right.
So it's not a, operational mission. So there is a mission now being drawn for atmosphere that's part of the decadal survey for aerosol, and one of the potential sensor, it's not even sure, would be a LiDAR. The question is, will this LiDAR have the capabilities we want for the ocean?
But how does the capabilities in the ocean degrade what they can do in the atmosphere?
They don't degrade, they just cost more money.
Okay.
And there might be more data. I mean, there might be, it might be bigger, so you have to have a different launch vehicle. It has logistic implication also on them. They have to be really nice to say, yes, we're willing to go through the pain it will cause us because we think the value for you is great for humanity and we should go for it. But I mean, these are the horse trading things that happen in backroom with lots of politics to make things like this happening. Yes?
To increase the vertical resolution, is it just a matter of having a higher higher sampling rate and maybe a stronger laser, or are there other physical?
Well, maybe it's a bigger detector too. You have to collect. You're limited by photons. So, and if it has to be eye safe, then you have to have a bigger, a source that's spread a bit more, and a detector, a telescope that's bigger.
How
And
much you
yeah.
have to send out shorter pulses, and they have to be higher, shorter pulses, and then you have to chop your signal coming back into the finer time resolution.
Which is small, a lower signal.
Yeah.
So then you have to increase your footprint or your antenna size or something.
So these are trade space. This is part of the trading space and for their science, they don't feel they need that.
How much smaller is 3-meter vertical resolution than what the atmosphere, the aerosol people would want? Do we-
30 meters is sufficient for them, and that's what they get from Calliope. They don't feel at least that they need higher resolution than 30 meters for the atmosphere. To know a cloud by 30 meters for them would be amazing.
All of this optimization stuff, if you look on the Ocean Optics web book, radiation transfer chapter level 2, there's a page called the LiDAR equation, where I derived this equation that shows you how your return signal depends on all of this, beta pi, aperture of your telescope, field of view of the telescope, in-water attenuation. Guess what? The beam spread function, we have a LiDAR beam propagating, it's going to spread out. And so that equation, you can play with it, plug in, if I have a smaller telescope and a bigger field of view and a, different beam spread function, et cetera, what do I get back to the satellite? So that's kind of the way people say, well, in order to get a detectable signal, I have to have, let's say, 10 to the minus 12 watts per square meter of irradiance making it back to the satellite. And now you can jiggle all your numbers around and see what you have to do to get that.
And again, so we're talking about the reiterating what Kurt just said, KD and BBP. The LiDAR does not measure KD or BBP. It's K system. It's the K of the system. It depends on your footprint. And it's the back scattering. It's really beta pi. And there's relationship. You're relating these to the KD from sunlight and beta pi to BBP. So there's conversion.
I remember what Kurt was saying about modeling does a terrible job at beta pi, right?
It's where the backscatter directions are most affected
By shape and
by
internal
shape
structure.
and non-homogeneities at beta pi. And you can also get a weird little effect called enhanced backscatter sometimes. That's from 179.9 to 180, the thing goes up by a factor of 2 or 3 in VSF. And so there's
Coherent
actually
backscattering. That's a
an
Schenker
instrument
thing.
built 20 years ago called the beta pi instrument, just to measure this beta pi from that last 1 degree from 179 to 180 to see how important these little effects were.
So that you can make that comparison from beta pi to BBP.
But what you see here is that whatever regression they put in, and it seems that the relationship relative to measurement in the field is not all over the map. It's constrained in your ability to get from a KD of an HSRL type LiDAR to the KD in the water. And these are all at 532. So we can constrain these either with observation, simultaneous observation, or try to come up with models that are more or less realistic to predict what it should be. And we used actually the measurements from Mafion from 20 years. We pulled out those SPIE paper to come up with what it might be or how much it's going to change. So if we now think about how can we improve and just getting more and more and more information out of a system like this. So this is what's in this table. So this is Calliope. We already have this. Now let's think about what it will take if we could get 3-meter vertical resolution. Then we're going to get profiles of KD backscattering, plus geophysical properties such as phytoplankton, the associate geophysical properties, better NPP, POC distribution, phytoplankton carbon. We can, and I'm not sure how that calibration error comes into play with the 3 meter. But what I assume it has to do is how much of the signal is very close to the surface or bubbles versus down or down below. And then the error in these two variables can be separated because again, we're getting them from one retrieval, but we have more in a water column distribution of these relative to each other. And for this, we add biooptical models or hydrolyte type thing to look at what we'd expect as change with vertical. Then there's, if we have the HSRL capability, so now we're separating these two completely. And depolarization at 1064. We have a continuous calibration throughout the profile. All this separation improves our geophysical products, and we're not dependent on biooptical modeling or ocean color simultaneously. That helps us anchor this difference between these two. We can add chlorophyll fluorescence. This just add one detector, and we can do it at night when it's not quenched. And we can compare night and day and get information about non-photochemical quenching. And it turns out that this is one of the methods by which you can tell if a population is iron stressed or not, by looking at its quenching behavior. So this gives you something about, is this environment responding to iron, and when in the year does it lack iron that will suppress its productivity and other things. And finally, you can also get, again, this is a fundamental frequency that you can get out of the 1064. If you add this one, now you have UV, you have CDOM. And on top of it, you can have, in the water, in two places, backscattering and KD. So now I have two wavelengths. I have 355, I have 532. I can separate better CDOM and pigment. I can get maybe a slope of particle size by looking at the ratio, because 532 is relatively deep in absorption. It's not a very strong absorption area. 355, there's not a lot of particulate absorption. And so, yeah, and finally, with this, improve resolve MPP. So this is the minimum stuff that we want to get to make it ocean. But this will not cost tremendously a lot to add. And again, there's all the numbers. But this is really the trade space that people are talking in back rooms and shouts and whatever in NASA. Yes?
So if you could get the HSRL, but not the 3 meter vertical resolution, that would still buy you a lot. So if you had to choose between any of those capabilities, I mean, yeah, it'd be great to have the vertical resolution, but there's also quite a bit to gain by doing the high spectral resolution. And that would be maybe less of a point of contention.
Yeah.
Right?
I mean, that's
The atmosphere.
I think they're most likely to go this way than
That's
they're
what I was
likely to
gonna
go
say.
this
So
way,
there's like the
whether we
engineering
want to.
requirement for ocean research, but I wouldn't say it's just Calliope Plus. I would say that HSRL is incredible.
I agree. I agree. Not only this is because these are not flown in vacuum. There is passive radiometry in the same time, and by using both, you can constrain, as has been done.
Great.
So, but you don't have the independence.
Great.
In terms of atmospheric, this one enhanced capability for cloud. So this is, we also have to try and convince the atmospheric community they want it. Better, more accurate profiles of aerosol extinction and backscatter with the HSRL. Improve aerosol typing and cloud condensation nuclei. Optical thickness of certain type of clouds. And more advanced cloud hydrophysics. So the HSRL brings much more to the atmospheric than these guys. Much more.
The depolarization, the cloud microphysics and stuff is
I assume, yeah, that's this. And finally, if you get the 355 as well, you have you can invert for more microphysical properties because you have more information, and from them it means getting effective radius of aerosol in NCCN, etc. But
And that turns around, and that really helps you in your atmospheric correction of passive, right? So it's enhancing pace.
yes, oh yeah, oh yeah,
Incredibly.
oh yeah. No, this will be amazing, but it costs money, and it means that you have to trade horses, and that's. But this is, I mean, I know most of you don't care about it, but it's stuff that you might get to play with when you grow up. So it's one. I mean, these are one generation investing in what the next generation will have to do science with, and so this is why it's important, because many of the people working on it will not be there when this thing flies. But they believe in it enough that they're willing to, go fight so that this is done. And it just takes time. From concept to flight takes tens of years. Yes, Colin.
So remember when you guys did the discussion on the Weeds paper and looking at vertical profiles related to surface caloric pressure? So imagine this flying in concert with the pace, and you can begin to test what that vertical distribution of phytoplankton is compared to that that's predicted by surface chlorophyll. And then you can begin to look at where do they match and where don't they match. And then, of course, you would also have community structure as well as size distribution as well as vertical structure. So think about the enhancement of local models for productivity. The potential is really incredible.
And also think about the separation of the pigment from the biomass, potentially. So you can say whether chlorophyll max is a biomass max or is it not? Is it just a pigment enhancement due to those things you can...
And another application, the whole LiDAR business is in the shallow water community. So remember yesterday, I was doing spectrum matching and I'm retrieving bottom depth and bottom reflectance in water IOPs. Well, if you also put a LiDAR along with your hyperspectral sensor, use the LiDAR to measure the bottom depth, then you don't have to retrieve that from the hyperspectral image, so you're constraining your retrieval, and you can now do a better job of retrieving the bottom reflectance and the water IOPs. And that was sort of the next step that the people I was working with were going to do when the economy crashed in 2000 and all the money went away. So I don't know what's being done out there. I know the USGS, US Geological Survey, was talking about flying combined hyperspectral and LiDAR sensors. The Navy was interested in it. They're probably out doing it now. And the people I was working with were interested in doing it. And so I sort of then got out of the field, and I don't know what's going on now, but that was the obvious next thing to do.
You talked about the footprint of the LiDAR in these things, that when you do the LiDAR mission, you're basically talking about one spot below, and so there's still room for all the models, because what you're doing is confirming a model in the center spot, if it's coupled with a...
It's a line, it's a curtain.
Yeah, if it's coupled with a passive where you have a spot, you've got it, you nail it in the center, and then you can serve this.
So in short, an ocean-optimized LiDAR, better understanding of polar and other problematic regions, major improvement in water column, phytoplankton stocks and rates, globally representative data for ocean color algorithm development, new information on physiology, if we couple it with fluorescence, ecological insight from day and night stock change, and Mike wrote a paper rejected from Nature as of last week, but hopefully it will be resubmitted soon, where he's finding significant changes in backscattering between day and night.
But you have a 16-day repeat. So you're not looking at the same spot day and night.
No, but you're looking at your night, your average night, and particularly next to the poles. But you're looking your average night over an area in time and how it changes compared to your average day. So you can say within these 2 weeks, how were my night value comparing to my day values in this real estate? And there's significant enhancement at night that cannot be explained by simple growth, which suggests that we're picking up signal from migrating organism entering into the surface layer. Anyway, so there's more science to do with this day-night variation, more accurate ocean color atmospheric correction, and active mixing depth of the ocean surface layer, so you can see when things are actually mixed versus a mixing. I think this is it. The rest is just additions. So here is the future constellation that Mike has envisioned. Is in combination with passive, you're having this, and Mike and others, you're having these guys. You also have BGC Argo in the water. There's now order several hundred sensor profiling floats with chlorophyll fluorescence and backscattering, and a slew of other, and nitrate and pH, and some of them have radiometers. And bringing these all together constrain the problem much better than any one of them can do on their own. And the hope is that this is going to happen. There's this mission called Mescal, which is really the sensor that the French are going to help put on the American satellite for ACE, whatever, the son of ACE, whatever it's called now. So that's the hope is that's the LiDAR, and the real hope is that this LiDAR will be made ocean capable in ways that provide our community more information than we currently get. But Calliope is a great example of the huge amount of information one can get by adding LiDARs to our toolbox. And the data is available, and I think it's on the Oregon State website where you can get the data from. Robert is the one doing some of the processing with Young, and it's available to you guys if ever you want to see whether in your area of the world bringing in the LiDAR is useful. Questions, comments? All good. So we're going to take a break until 10:15. We have Catherine here. She's a young scientist now at Bigelow, and she's going to be our next stop. See you at 10:15.